So we need to find the rate at which coal must be burned, and then how much the rate at which the mass rate of water in order to cool. So we have the efficiency. This is going to be 65% of the efficiency of the Carnot engine. We have the temperature of the higher region of the first system. This is going to be 750 degrees Celsius, or we can say 1023 Kelvin. We simply need to add 273 to the degrees in Celsius in order to convert to Kelvin. T of L1 would be 440 degrees Celsius, or again, 713 Kelvin. TH sub 2 is going to be equal to 415 degrees Celsius. This is equal to 688 Kelvin. And then we'll have T sub L2 is going to be equal to 270 degrees Celsius, or 543 Kelvin. So here we also know we have 2.8 times 10 to the 7th joules per kilogram of coal. So for part A, we need the burn rate of coal. So we can say that A is so part A, we have the efficiency of the first system is going to be equal to the 65% of the efficiency of C2, or rather C1. And this could be 6.65. This will be 1, we'll say 1 minus, and then this will be TL sub 1 divided by TH sub 1, like that. And we can solve, so E sub 1 is going to be equal to 0.65, 1 minus, and then this will be 713 divided by 1023. And this is going to give us 0.197. E sub 2 is going to be 0.65 E Carnot 2. So this will be 0.65. And this will be simply 1 minus T sub L2 divided by T sub H2. So we have that E sub 2 is going to equal 0.65. And then this will be times 1 minus 543 divided by 688, and this efficiency will be 0.137. At this point, we can find the work done by the first system. This will be equal to E sub 1 Q sub H1, and this is going to be equal to E sub 1 Q of coal. We know that Q sub L1 equals Q sub H1 minus the work sub 1. So this will be equal to 1 minus E sub 1, and then times Q of coal. Now we can relate and say that work sub 2 equals E sub 2 Q sub H2. This is going to equal E sub 2 Q sub L1, and this will equal E sub 2, 1 minus E sub 1, Q of coal. So we can then add these and say that work sub 1 plus work sub 2 is going to equal E sub 1 Q of coal, and then plus E sub 2, 1 minus E sub 1 Q of coal. And we are getting that this is going to be equal to Q sub coal, and it'll be E sub 1 plus E sub 2 minus E sub 1 times E sub 2. So Q of coal, rather let's get a new workbook. Q sub coal is going to be equal to work sub 1 plus work sub 2 divided by E sub 1 plus E sub 2 minus E sub 1 E sub 2. So we can simply say Q of coal over T, which is we're trying to find how much it should be burned, trying to find what's the burn rate of coal. So this will be equal to work sub 1 plus work sub 2 per time. And then again, E sub 1 plus E sub 2 minus E sub 1 E sub 2. And we can actually substitute. So Q sub coal T will equal 950 times 10 to the 6th, or 950 milliwatts. And then we'll have 0.197 plus 0.137 minus 0.197 times 0.137. And we need to convert. So this, first of all, this is going to equal 3.094 times 10 to the 9th joules per second. And we should convert. So Q coal sub T will equal 3.094 times 10 to the 9th joules per second. And then we can say times 1 kilogram for every 2.8 times 10 to the 7th joules. So this will equal 110.5 kilograms of coal per second. So this would be the burn rate of coal. Now it's saying for part B, we need to cool it down. So how much water is needed? So part B, we can create a relationship and say that the Q exhaust is going to be equal to the Q of coal minus the work. So this is simply another way of saying Q sub L. And so we have Q sub coal minus W, and this is going to equal the mass of the water times the specific heat of the water times the change in temperature of the water. So we have that the mass of H2O is going to be equal to the Q exhaust divided by C sub H2O times delta T of H2O. And this will equal Q of coal minus W divided by C sub H2O delta T sub H2O. At this point, we can divide by time. So if we divide by time, we can say that mass of H2O divided by T is going to equal the Q of coal divided by T minus work divided by T, all divided by the specific heat capacity of water times delta T of H2O. And at this point, we can actually substitute. So we can say 3.094 times 10 to the 9th. And then we'll have 9.5 times 10 to the 8th. This will have to be minus, apologize. All divided by 4,186 joules per kilogram per Kelvin, and then the change in delta T will simply be 4.5 degrees Celsius. So we're getting that the mass of H2O needed per second would be 1.13 times 10 to the 5th kilograms per second. So this would be our needed. Now we need to convert to gallons per hour. So we can simply just say 1.13 times 10 to the 5th. This will be kilograms per second. And then we can say times 3,600 seconds per hour. We know that the density of water, 1 meter squared divided by 1,000 kilograms. And we know that there's 1,000 liters in every cubic meter. And we can say that this is also times 1 gallon equaling 3.785 liters. So at this point, we can simply solve, and we find that the mass of H2O per unit time is going to be equal to approximately 1.1 times 10 to the 8th gallons of water per hour. So this would be our final answer for part B. That is the mass flow rate, essentially, of the water. That's the end of the solution. Thank you for watching.